In this segment, we're going to begin to identify crystals using the petrographic microscope. There are two general kinds of crystal materials that we'll look at. First kind is called isotropic, which includes minerals of the isometric crystal class. And the second kind is called anisotropic. Anisotropic crystals are subdivided into two groups called uniaxial and biaxial groups. And we'll talk about the distinction of these two groups later. In this particular segment, we're going to concentrate on identification of isotropic minerals, and in later tapes we'll talk about anisotropic, both uniaxial and biaxial varieties. To give you an idea of the proportion of minerals of each type, isotropic minerals make up only about 15% of minerals found in nature. Uniaxial minerals about 21%, and the overwhelming majority of minerals are biaxial, the most optically complex. But we're going to start again concentrating on this simple subgroup of minerals and properties associated with their identification. Now, the optical subdivision of minerals is very closely tied to crystallography. As I said, isotropic minerals are from the isometric crystal system. And as the symmetry becomes less in these minerals, that is, as we go to less symmetrical groups, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic, the minerals become more optically complex as well. Uniaxial minerals include both the tetragonal and hexagonal crystal systems, while biaxial minerals include orthorhombic, monoclinic, and triclinic crystal systems. Well, if we're going to apply techniques of identification of isometric minerals, we have to know how to recognize them, and so I'm just going to review for you the way in which we recognize isotropic crystals. There are two steps to this. First is to, with the specimen on the stage, to flip in the microscope analyzer. That allows you to examine the crystal in crossed polarized light. And the second step is to rotate the stage of the microscope, which moves the orientation of the crystal, and you are really looking for whether the crystal is illuminated during that stage rotation. The test then is that isotropic minerals will not be illuminated at any rotation position or in any orientation between cross polarizers, whereas anisotropic ones will become illuminated in most orientations. Well, let's make a test like this within a thin section that includes some isotropic minerals to demonstrate its utility. So I've got a thin section prepared here of a garnet-bearing schist. Of course, garnet is a member of the isometric crystal class, and it's a good isotropic mineral. And so if we look at this specimen in the plane polarized light, which we're doing now, you can see the definition of particular mineral grains. Now, most of the minerals in this rock, as they are in nearly all rocks, are anisotropic. Now, if we want to distinguish anisotropic from isotropic minerals, we should again cross the polars, as I've done now, and we look at the distinct mineral grains during rotation to see which ones are illuminated during most parts of the rotation. You can see most of the minerals, including the ones that I'm pointing at, are illuminated during most of the rotation periods, but we do have these large equidimensional masses that remain dark. These are the garnets within the rock, and this demonstrates the method of distinguishing isotropic from anisotropic using the petrographic microscope. So we have anisotropic and isotropic minerals. Now, another example I have, for example, I have a prepared mount of grains of the mineral halite, which is another isotropic mineral. And again, if we look at this in the plane polarized light, you can see the outline of the cubic halite crystals. And I just point out that the shape, the dodecahedral shapes of garnets and the cubic shapes of halites are very important identification criteria. And if you can see crystal form, this can help you identify what particular minerals these are. Halite, of course, shows this very nice cubic crystal form that you can see here in plane polarized light. And if I cross the polars, again you see the halite, and even during stage rotation, and cross and uncross the polars here to demonstrate the rotation. The halite is not illuminated in any rotation position, so it shows very good isotropic optics. Now, some other properties we can use. We mentioned crystal form as an aid to identification minerals. Some other properties that are useful are things like the cleavage of the particular mineral. For example, let's look at a specimen of amphibolite. Amphibolite is a made up largely of hornblende, this particular rock. Now, the hornblende is not an isotropic mineral, but it allows us to look at a very good example of cleavage within a particular mineral. And here I'm pointing out the very well-developed cleavage forms within these amphibole grains. And you can see that this particular mineral, the amphibole makes about a 60-degree, 120-degree intersection within two prismatic cleavage forms within the crystal. And this is a very useful parameter for its identification. Well, many isotropic crystals show cleavage as well, and cleavage is a very useful parameter that you can see in all kinds of minerals and should not be ignored if it's present as a identification criteria. Another property of identification that we commonly use is color. Now, color results in minerals when white light, which comes from below the stage of the microscope, is absorbed by the mineral during the time that the light passes through it. And the absorption of light by a mineral results in subtraction of particular wavelengths from the white light and results in color. Just as a demonstration of this, I'll take a look at the mineral biotite, and this is a biotite-bearing granite. And again, we're looking at the mineral in plane polarized light because that's where the property of color is observed. And you can see that the biotites, which I'm pointing out now, are clearly brown or reddish brown in color. And the intensity of this color varies a little bit upon rotation, but the color is due to absorption, differential absorption of different wavelengths of the white light. And this color is obviously very distinctive for the biotite. And different minerals, particularly those that have iron or other elements within them, have a tendency to absorb some of the visible wavelengths and impart a strong color in transmitted light. So we use this color to aid in identification. Well, so these are some of the properties then that we can use for identification in isotropic minerals. I want to give now a definition of the term isotropic, which we can apply and really make a distinction from anisotropic minerals. In isotropic substances, light travels the same speed in all directions. And this is not true for anisotropic minerals. So a very simple way to explain what isotropic materials are. In most crystals, because of the crystal structure, it's just simply not as easy for light vibrating or propagating in one direction to travel as rapidly as it can in other directions. Now, what are some isotropic materials? Well, a lot of familiar substances behave isotropically with respect to light. Air is certainly effectively isotropic, water, glass material, and of course isometric crystals. Now, some of these things are important. It's certainly important that air is isotropic because air is in the path of our microscope, and it could cause us problems if this were the case. And also it's important that glass is, because we use glass slides and glass cover glasses as part of our optical equipment. It's also true that not only water but immersion liquids that we use commonly as mounts and things like Canada balsam are also isotropic. Well, I want to concentrate on a particular property of isotropic minerals, and this is the relief, and to show you how to determine relief within a prepared mount. Relief has to do, of course, with the index of refraction of the substance. And I just review this definition of the index of refraction. The index of refraction of any substance, for example X, is simply equal to the ratio of the velocity of light in a vacuum over the velocity of light in that particular substance. And relief then is defined as the absolute value of the difference between the index of refraction of the material of the mount, that is usually a liquid or an epoxy. So it's the absolute value of the difference between that index of refraction and the index of refraction of the crystal that we're effectively examining. Now, if we want to evaluate relief, we can do so by looking again at boundary effects. This is something we did in the last tape, where we examined really the strength of the refractory effects around the boundaries of crystals, and we made a distinction between some different recognized kinds of relief based on the observation of boundary effects. Low relief, which is characterized by very, very minimal effects around the boundaries of the grains. Moderate relief, where the grains become very well defined. And high relief, when the boundaries become extremely broad and subject to strong refractory effects. Sometimes the grain shows extremely high relief, as most crystals do in air, and we can think of a fourth category of extreme relief, which is actually rarely perceived in most prepared mounts. Now, it's possible also to talk about relief in terms of whether it is positive or negative. And the distinction here between positive and negative relief is shown here. What is the relationship between the index of refraction of the mounting material and the index of diffraction of the crystal? There are two possibilities. One is that the index of refraction of the mounting material is less than the index of refraction of the crystal. And this, by convention, is called positive relief. Now, positive relief means that another way of saying this is to say that the crystal is high. The crystal is higher than the material surrounding it. Negative relief is just the opposite, when the index of refraction of the crystal is less than the index of refraction of the mounting medium. Remember then, this means that in the case of negative relief, that light travels faster in the crystal than it does in the material surrounding it. Now, in the thin section, which is the most common kind of prepared mount that we deal with, relief, there's a special solution to relief, because the index of refraction of the mounting material is always fixed at this value of 1.54. And so relief in thin section is a special solution of the relief equation, where it corresponds to the absolute value of the difference between the 1.54 and the index of refraction of the crystal. Now, it turns out that we use adjectives like low negative or moderate positive to characterize relief, and the first modifier, low, moderate, or high relief corresponds to how large this difference is. Again, following the guidelines that we've established. And the words negative or positive then would refer to whether the index of refraction of the crystal is higher or lower than the index of refraction of the mounting material. Okay, now how do we determine if a mineral has positive or negative relief? We know something about how to estimate the degree of relief, but how do we determine the sign of relief? Well, there are two good methods, and I'm going to demonstrate these methods using some immersion mounts. So the first thing I want to do is I want to take a particular mineral and I want to make an immersion mount of that material. So here's the materials I need. I'm going to take an immersion liquid here that has an index of refraction of 1.576. And I've got a glass slide here with a cover glass. And on this glass slide then I'm going to combine these kinds of materials. And I'm going to take my mineral grains, which are stored here in a vial, and transfer some of them to this mount and combine it with the index of refraction liquid. So I'll just extract the mineral grains here. And place them on the glass slide, just a few of them. And actually, you rarely, if you're dealing with isotropic minerals in particular, you don't need many of these mineral grains at all. I've put about 15 or 20 of these mineral grains on the slide, which is plenty for isotropic minerals. And then I'm going to bathe these mineral grains located in this part of the slide with the immersion liquid. Before I do that, I'm going to place the cover glass over the top of these mineral grains. And so now I have mineral grains covered with the cover glass, and mostly there's open space between the cover glass and the glass slide. And I'm just now opening the immersion liquid, and I just touch the edge of the gap with the immersion liquid, and it begins to bathe the grains that are located between the cover glass and the glass slide. So now I've prepared an immersion mount, and most of these mineral grains are completely bathed in an immersion liquid. And I remind you again that the index of refraction of this liquid is specified right on the bottle. And so what I'm going to measure then is whether the mineral grain has an index of refraction that is higher or lower than this value. And I'm going to look at the boundary around the grains to see how much higher or lower these particular mineral grains are. And that's the strategy of using immersion mounts to narrow down the refractive index of a particular mineral grain. So I'm going to take this mount and I'm going to place it on the microscope stage here, and we're going to illuminate the mineral grain here. We're looking at it here with a medium power. I'm going to apply a test now that's called the central illumination test, or sometimes it's called the Becky line test. Now, in order to do this test, we want to look at the mineral in plain polarized light. That is, we have the analyzer out. One special thing seems to help, and that is that if you can adjust the diaphragm in the lower part of the stage to make the light a bit more divergent, the central illumination test works better. And so I've done this, and now we're taking a look at the mineral grain, and as I look at the mineral grain, I'm going to adjust the focus. And the sense of adjusting the focus is very important. That is, I want to move my focus so that the stage of the microscope has a sense of movement that effectively lowers the stage. The stage moves, and in some microscopes the tube of the microscope moves and then would be raised. So whichever sense you use, you want to think of either the stage being dropped or the tube of the microscope being raised. That is, you're raising the plane of focus of the microscope as you look at the specimen. So we're going to effectively move the stage down, and as we move the stage down, we want to look at the edge of these mineral grains. That is, the refractory effects that occur at the edge of the mineral grain. So now I'm raising the focus of the microscope. I'm lowering the stage of the microscope. And I think you can see, in fact, I'll point it out using a pointer arrow on the image showing a very bright illuminated ring around the mineral grain, which as I lower the stage, as I'm doing now, as I raise the plane of focus, as I'm doing now, this particular line moves out of the crystal. You can see that the line is moving out of the crystal as I raise the plane of focus of the stage. And this is the Becky line, the central illumination test. And when this line moves out, when I make this sense of movement, and I raise the focus and the line is moving out, this tells me that the crystal has a refractive index that is lower than the refractive index of the mounting medium. Since the mounting medium has a refractive index of 1.576, then I now know that the refractive index of this mineral is less than 1.576. Now, so this is how I tell the difference between positive and negative relief. And this particular mineral in this mount shows negative relief. Now I have another mount prepared, and this particular mount is prepared in a different refractive index oil. Here's this second mount. It's the same mineral, but this time I've changed the refractive index liquid to a index of refraction of about 1.478. So it's quite a different refractive index. And I actually chose this value because I could see that the relief in the previous specimen was moderate relief, and so I wanted to change the index of refraction at least enough to hopefully to reduce the relief from a moderate level. So I have now a new mount, the same mineral, now mounted in a different index of refraction liquid. And I'm going to take this mount and again perform the central illumination test on this. So I've got the mineral grain again, observing it in plane polarized light, and I'm now lowering the stage, raising the plane of focus, lowering the stage, and here I think you can see that the sense of movement of the Becky line in this central illumination test is the opposite. Now the Becky line is moving into the mineral grain as I raise the focus. I'm now raising the focus, lowering the stage, lowering the stage. The Becky line moves into the middle of the mineral grain. This indicates that the refractive index of this crystal is now higher than the refractive index of the mounting material, or we can say it has positive relief. And we can also see in this mineral grain that the crystals have a bit lower relief. They're now characterized by low positive relief in the first mount. They had moderate negative relief. So we can characterize both the sign of the relief and the degree of the relief by careful observations. And our objective really is to close in on the refractive index of this isometric mineral. Since light in an isotropic mineral travels the same speed in all directions, then we can describe its optics by one unique refractive index. And this mineral is isotropic. It has one refractive index. And now we know that this refractive index is between 1.478 and 1.576. And indeed, we know also that it is closer to 1.478 by our observations. And so our objective then would be to close in by continually changing the index of refraction of the oils until we can identify precisely what the index of refraction is of that mineral. And the index of refraction is very specific for individual minerals. So by characterizing the relief, it's a very, very good way to identify a particular mineral. So we've now demonstrated the central illumination test. But why does a central illumination test work? I want to give a simple explanation of why the Becky line moves in the sense that it does. And so I'll do that using a simplified drawing like this. The point here is that what I've done is illustrated something that occurs completely within the immersion mount. That is, the whole area that I'm showing here is within the immersion mount. And this area here surrounding the crystal represents the immersion liquid. And this black outline represents a crystal. It's a very idealized form, but the important thing about it is that most of the time when you look at mineral grains, they are thinner at the edge than they are in the center. And as long as that's true, and that's true for nearly all grains, then the Becky line test will work. And so what happens is I'm showing the direction of propagation of light, which goes this way through the crystal, and in the central part of this crystal, if the top of the crystal is flat and the bottom is flat, then light goes directly through it. There is no difference in the angle of incidence and the angle of refraction. But if there's an angle, as there is in the thinner parts of the edges of the crystal, then the light is actually refracted at the edges. And when we raise the plane of focus of the microscope, I can show this by using another card on this diagram. By raising the plane of focus in the microscope, you can imagine what parts of the crystal you may be seeing. If the focal plane is below the crystal, you don't see the effects of the crystal, but as we raise the plane of focus of the crystal, then our perception is that the edge of the crystal tends to move toward the outer margin if the crystal has a lower refractive index than the material surrounding it. So the Becky line, for the case of negative relief, the first example that we looked at, works effectively like this, in that the edges of the crystal appear to diverge when you raise the plane of focus of the microscope. Now the opposite is true if the refractive index of the mineral is higher than the refractive index of the surrounding material. Here's the case then of the crystal being high, and the effect of raising the plane of focus of the microscope, you would observe the Becky line moving in toward the central part of the crystal. So this is the explanation, really optically, of the Becky line test, or central illumination test. Well, there's another way that we can, another test that we can perform to get the sign of relief. And this test is called the oblique illumination test. And for the oblique illumination test, we use a similar kind of optical setup. And one of the things that I'll repeat this test now using both of our mounts. I'll start with the case which we observed before, where there was negative relief. We're looking at this mineral in a 1.576 oil. Now, what we'll do in this particular test is I'm going to open the diaphragm again here to increase our light, and I'm going to use the accessory slot and an accessory plate. So I'm going to use this accessory plate. It doesn't matter which accessory plate you use. You can use your gypsum or your mica plate. And because we don't put it in the accessory slot all the way, I'm going to put it in, slide it in the slot light like here, just enough so that the leading edge of the accessory plate blocks the normal path of light that's coming up through the tube. If we look now at the specimen, you can see that part of the field of view of the specimen has become dark. And the way we apply the oblique illumination test is to observe the shadowing on the mineral grains. Now, if you look at the shadowing on these particular mineral grains, you can see that one side of the mineral grain is bright, another side of the mineral grain is dark. Now, we look at the shadowing and the shadowing on the grain with respect to the shadow within the field of view. Now, in this particular case, with our high index oil and with the crystal of lower index, the shadow on the mineral grain, which I'm pointing to now, is opposite to the shadow in the field of view. This case we call shadow opposite, crystal low. This means the relief is negative. Okay, so this is the oblique illumination test applied, crystal low, shadow opposite. Now what I'll do is I'll shift now using the same, leaving the accessory plate in the same kind of position. I'll shift to my other mount, back to the 1.478 oil, and look at the other case of oblique illumination. Here now, looking at these grains, you can see that the shadow is on the same side as the shadow in the field of view, or the shadow is near rather than opposite, we say. If the shadow is near, then the crystal is high and the relief is positive. So again, this is a redundant kind of test, and what you find is that for some grains, using the oblique illumination test is much better, much easier to see the result than using the central illumination test. So you can use either depending on whether these grains are suitable for one test or the other. Or if there's some question about the result, you can perform both tests to test the relief of particular mineral grains. So this is the oblique illumination test demonstrating positive and negative relief. Well, now we want to get closer to the refractive index of this crystal. And so I want to demonstrate what happens when you get very close to a match between the crystal and the immersion liquid. And so let me show you, I've prepared already a couple of mounts. And these two mounts are the following. First one is a mount in an index of refraction oil of 1.488. This is a little bit higher. It's about 0.01 higher than the last mount which we made. And here's our, again, prepared refractive index mount. And the second refractive index mount that I've made is in a slightly higher oil of 1.492 refractive index. So we're going to look at these two mounts, which actually bracket the refractive index of this particular mineral. One is very slightly higher, one is very slightly lower than the refractive index of this particular mineral. So let's look at these two mineral mounts successively. So first we'll look at the 1.488 oil, and I'm going to concentrate now on applying, well, first I'll try the Becky line test to show you what these mineral grains look like. So I'll extract the accessory plate and close the diaphragm here in order to apply the Becky line test. So here are mineral grains now bathed in an oil that's very, very close to its refractive index. And I'll point out the edges of these mineral grains. You can barely see these edges. They have extremely low relief. And as I raise the plane of focus, you may be able to discern very slight colored Becky lines which are observed in this particular mineral grain. That is, we're beginning to see very slightly colored Becky lines in this particular mount. And so the combination of having very, very small boundary effects and having colored Becky lines should lead you to apply the oblique mineral test. And so I'm going to do this. I'm going to open a diaphragm again and put in our accessory plate into the accessory slot until part of the field is blocked. And now I want to look at the colors that I see on the edges of grain. These mineral grains show around their edges now what we call color fringes. These color fringes happen and occur when the mineral grain is very close to the refractive index of the mounting liquid. These particular color fringes are slightly yellow in color. There actually are also greenish and violet fringes, but if you look at the ones on the yellow to red end of the spectrum and pay attention to the character of these colors, you get an idea of how close to the refractive index we're dealing with. So in the 1.488 oil, we have yellow color fringes, and this indicates that the refractive index is very, very slightly higher than the refractive index of the mounting liquid. So that we could make a guess then that we'd have to change only by a very, very small amount this refractive index. These color fringes happen only when you are very, very close to a match of refractive index. Now let's look at the other mount now. We'll go to the 1.492 mount and have a look at the color fringes that we see here. Again, I just leave the accessory plate in the slot here. We'll look at the colors now on the edge of these mineral grains. And here they are. And I think you can see now that the color fringes are brownish in color, distinctly different from the yellow color fringes that we saw before. This means that the refractive index of this particular unknown mineral is just slightly lower than the refractive index of the mounting liquid. And this is a 1.492. So we know now that the mineral has a refractive index slightly lower than 1.492 and slightly higher than 1.488. Well, what happens if we get a precise match? And so I've made a final mount now using a refractive index liquid of exactly 1.490. And let's look at this mount and apply our oblique illumination test. When we're very close to a match, the oblique test is the best test to perform, and we're really looking at the color of these color fringes. So here now, looking at the mineral grains, you can see that the color fringes have a very distinct orange-red or red-orange kind of color. And this color is very distinctive of a precise match of the refractive index of the liquid with the refractive index of the crystal. And so if we have an unknown isotropic mineral, we can make continued tests in immersion, applying the oblique illumination test in the final stages, the central illumination test especially in the early stages when we're farther from a match, in order to estimate what the refractive index of that material is. When we find an oil that precisely matches the liquid, we should test the refractive index of that oil with the Abbey refractometer, as I've demonstrated before. One reason we need to check the refractive index of oil is because it's strongly temperature dependent, so that any particular refractive index that you see on a bottle is subject to room temperature variations, and the refractive index of these liquids are quite sensitive to these kinds of changes. They're also sensitive to evaporation that can happen if the bottle is not tightly sealed, so they do need to be measured. Just as an example of this, I've got this mount on a hot plate, and the hot plate is turned up so that I'm actually heating the mount now to raise the temperature of the immersion oil. So if I take this, which is sat now for 30 seconds on the hot plate, you can see a very noticeable difference in the oblique illumination test for this particular mount as we observe it now with the microscope. So I'll move the microscope back. We'll again apply the oblique illumination test on this particular mineral. And as we look at the mineral grains, I think you can see now, even though we have the same refractive index as before, 1.490 as listed on the bottle, the heat has actually lowered the refractive index of the liquid, and now we see a yellow color fringe that indicates that the crystal is slightly high. Well, I have left to explain why we develop these color fringes when we're very close to a match. And so these last diagrams demonstrate why color fringes occur. And let's consider first of all the case where we had yellow color fringes. This plot shows the relationship between refractive index and wavelength. And because of the nature of the substances, there is a difference in the way refractive index changes as a function of wavelength. Over on this side are short wavelengths of violet and blue light. And over on this side are long wavelengths of red light and orange light. And the yellow, which is right in the middle of the visible spectrum, has its wavelength located approximately here where the pencil is located. Now, it is the nature of refractive index liquids that they have a very steep slope on this kind of plot, that they're very sensitive to, there's a very dramatic change in refractive index with wavelength for the liquid, and it's very much more gentle slope for the crystal. So when yellow color fringes occur, the match occurs way in this end of the visible spectrum, and for yellow light the crystal is high. So we see yellow color fringes. Now for the brown color fringes, we have exactly the opposite kind of situation. Again, the yellow light is located here in the middle of the spectrum. The match occurs on the red wavelength side. So we see brown color fringes in this particular case. Highly variable refractive index with wavelength for liquid, much low variation for crystal. And the case of the perfect match is shown here, where there is a match of the refractive index of the crystal and the liquid right in the center of the visible wavelength. And here we see color fringes that correspond to red-orange colors, respecting this part of the range of color schemes. There is in fact another color fringe that corresponds to blue-green that occurs to this side. But if we watch the red-orange, yellow, or brown color fringes, we get a very good index of this position of the match. And so now we're in a position then to evaluate the relief and the various other properties of isotropic minerals.